All right, today we're putting on our detective hats. We're going to solve a classic mystery, one that drives developers absolutely crazy. Why is this code so unbelievably slow? Stick around, because by the end of this, you'll have the tools to be a code detective yourself. Let's get into it. I mean, we've all been there, right? You get handed a piece of code, you run it, and suddenly you've got enough time to go make a coffee. Maybe two. It's a huge headache, whether you're a developer, a product owner, or a tech manager, especially when you're dealing with those big legacy applications. So, our case file today is all about a program we'll call Slow Code. It was written by a developer, we'll just call him Mr. Smith. This program is our prime suspect for some serious performance issues, and it's our job to dig through the evidence and figure out exactly what's going on under the hood. Now, to solve a mystery like this, you need the right tools. And for a performance detective, the most important tool in the entire toolkit is something called Big O notation. Think of it like our special magnifying glass. It lets us see exactly how an algorithm behaves as the amount of data it has to chew through gets bigger and bigger. So what is Big O actually measuring? Well, it all comes down to this idea of time complexity. We're not talking about seconds or milliseconds here. Instead, we're describing the relationship between the size of the input, let's call it n, and the number of operations the code has to do. Does the work stay flat? Does it grow nice and steady? Or does it just explode? And this slide, wow, it shows you just how dramatic that difference can be. Over on the left, you've got O of n, or what we call linear time. As your input n gets bigger, the runtime grows right along with it. Totally manageable, totally scalable. But on the right, you've got O of n squared, or quadratic time. This is where the runtime grows exponentially, and that is usually where our performance mysteries begin. Okay, so we've got our magnifying glass, and we know to be on the lookout for that dangerous O(n) squared pattern. It's time to examine the scene of the crime, the code itself. We're going to follow the trail, line by line, and hunt down those performance bottlenecks. Our investigation kicks off inside a function called slow method. Right away, we spot a loop. It runs n times, where n is just the input number. On its own, this gives us a complexity of O of n. So far, so good. Nothing too scary here. But hold on, the really interesting part is what's happening inside that loop. For every single trip through that first loop, it calls another method. This one's called element and data divides. And when we look inside that method, we find our second major clue, another loop that goes over the data again. And this right here is the smoking gun. We have a loop running n times, and for each of those n times, it's running another loop that also runs roughly n times. We're basically doing n things n times. What does that give us? A combined complexity of O of n squared. We've found our first major performance thief. To really get how bad O(n) squared is, just look at this quote. If you increase your input by a factor of 10, like going from 1,000 items to 10,000, the runtime doesn't just go up by 10. Oh no, it goes up by 10 squared. That's 100 times longer. The slowdown is just brutal, and it gets worse incredibly fast. And the plot thickens even more. As we keep digging, we find another method called filter that slow method also uses. And guess what? It's a repeat offender. It has the exact same problematic pattern, a loop that calls that same super expensive element in data divides method. This isn't just one little mistake. This is a systemic issue baked right into the code. Now, you might notice the filter method does some other stuff, like converting numbers to strings. That operation has a complexity around O of n log n. And while that's not perfect, when you've got a giant flashing O of n squared problem, an O of n log n issue is basically like worrying about a leaky faucet during a flood. We gotta focus on the biggest offender first. Okay, we've gathered all the evidence. Now it's time to put it all together and see who, or, well, what, is really responsible for making this code so slow. Let's line up the suspects. So here it is, our official list of culprits. Number 1, the main villain, is that nested loop structure that gives us the dreaded O of n squared complexity. That makes element and data divides the single most time-consuming part of the whole program. We also found some accomplices, like an inefficient way of adding to an array, and even a misleading prompt for the user, which just points to some sloppy design. All right, the culprits are identified. The case is pretty much closed. But the most important part of any investigation is figuring out what we can learn from it so we don't make these same mistakes again. Let's look at the final verdict and the big takeaways. The case file summary makes it crystal clear. Both the slow method and the filter method loops are found guilty of O of n squared complexity. That string conversion stuff, a lesser offense. The verdict for the program as a whole, critically inefficient. The evidence is just overwhelming. So, how do you avoid becoming the next Mr. Smith? Well, here's your guide. First, be super suspicious of nested loops, especially with big sets of data. Second, find out where your code is spending most of its time and focus your energy there first. Third, use smart data structures. And finally, the biggest lesson of all, think about Big O before you even start writing the code. And with that, we close the case of the slow code. Mystery solved. But it does leave one final question for you. Now that you have the detective's toolkit, what performance thieves are hiding out in your code?